Hi everyone, in the last session we talked about how to calculate the hydronium ion concentration or the Ka for a weak acid. Okay, now here we're going to talk about polyprotic acids, meaning acid with more than one ionizable proton in solution. Each dissociation step has a different value for Ka. Now for example, if you take H3PO4, which is phosphoric acid, so the three hydrogens, they dissociate one at a time. Now once the first hydrogen lost, it would become H2PO4 minus and hydronium ion. So if you write the Ka1 for that, it's going to be your products over reactant. Again, we are only putting H3PO4, right? Hydronium ions times H2PO4 minus, and the Ka1 for this is 7.2 into 10 to the negative 3. And for the second dissociation, you start with the next one, which is once the hydrogen is lost, what you left is the conjugate base of the phosphoric acid. You start with that, and then you lose another proton from here, giving you HPO4 minus 2, because you had 2, right now you have only 1. So the charge of the acid will become negative 2, which is your formal charge, and hydronium ion. So the Ka2 would be the products, again these two over reactant, this one, 6.3 into 10 to the negative 8. Notice here the acid strength decreases for each ionizing proton, right? The first one normally is the strongest one, and then acid strength decreases. So the third one, HPO4 minus 2, where you start from where you stop, lose the last hydrogen, become phosphate ion and hydronium ion. So if you write the Ka3, there would be hydronium times phosphate over HPO4 negative 2. And then this is the acid dissociation constant. So you can see Ka1 is way more than Ka2, which is way more stronger than Ka3. Normally the first ionization is the most stronger one, and then it decreases. Okay. And these are some Ka values for some polyprotic acids. Oxalic acid has 2 ionizable hydrogens, always Ka1 is greater than the Ka2. Sulfurous acid H2SO3, not sulfuric acid. Sulfuric acid is a strong acid. Again, there are 2 ionizable protons, so these are the 2 acid strengths. Phosphoric acid, we talk about that. So here it is arsenic acid, carbonic acid, hydrosulfuric acid. So you can see each of these weak acids, they have different Ka values, and always the Ka1 is stronger compared to the Ka2 or the Ka3. Okay, and decreases acid strengths. Okay, now we're going to look at another category of acids, and they are called non-metal hydrides. Non-metal hydrides. So what are these non-metal hydrides? So they are like H2S, or they are like H2O, or it could be hydrogen fluoride, HF. So those are non-metals. Remember, oxygen, sulfur, fluorine, they are all non-metals, and they are with the hydrogens, they can form acids. So now we're going to compare acid strengths of non-metal hydrides. For non-metal hydrides, E is the non-metal, H is the hydrogen. Acid strength depend on the electronegativity of the central non-metal. Now the non-metal here in these 3 examples, oxygen, sulfur, fluorine, we're going to look at the electronegativity, right? Which one is the most electronegative element in the periodic table? It is fluorine, right? Fluorine electronegativity is 4.0, which is like your GPA, correct? So that's the fluorine. And then also it depends on the strength of the metal and the hydrogen bond. If it has a very strong bond, it would become difficult for hydrogen to donate, right? If you have a weak bond, so then the acid strength will increase because it's easy to give away that hydrogen. Okay, so across a period, acid strength increases. So remember the periodic table, okay, over here also. And come on. Across a period, acid strength increases. Why? Because the electronegativity increases across a period. So the most electronegative element is fluorine. And in group, in period 2, what do we have? We have boron, carbon, nitrogen, oxygen, fluorine, like that, right? And then the next one we have sulfur, chlorine. So as you go across the periodic table, electronegativity increases. Now if you take the hydrides of oxygen and fluorine, hydride of oxygen H2O, hydride of fluorine HF. So fluorine is more electronegative compared to oxygen. So HF is going to be a stronger weak acid compared to water. Okay, as the acid strength increases, as the electronegativity increases. So as a result, across a period, acidity increases. Now if you take sulfur and chlorine in the period 3, right? So you have H2S and HCl, hydrides. Now these two, sulfur and chlorine, they both are in the same period. Which one you think is a strong acid? It's the hydrochloric acid, which is again a stronger acid, so acid strength increases. Okay, I will show you that in the next slide also. What happens as you go down a group? As you go down the group, acid strength increases. How does that happen? Because the bond length of the metal hydrogen bond increases down the group, and its bond strength therefore decreases. So what does that mean? So as you go down, let's say you go down in the periodic table in terms of, let's say we take H2S, sulfur, and then you have selenium, and on top of that we have oxygen, sulfur, selenium, tellurium. And what happened to the size of the atom as you go down? Size increases. Remember, size increases as you go down the periodic table. So the smaller size is getting bigger, bigger and bigger. And then you have a hydrogen attached to this, like that. So as the bond length increases, strength decreases. If the bond strength is decreases, it's easy for hydrogen to move away from the atom and break the bond. So you can see the length of the metal hydrogen bond increases down a group, and its bond strength therefore decreases. As a result, as you go down the group, acid strength increases. Okay. Now you can see that with numbers in this table. Let's see as you go across the periodic table. Water is not an acid. Water is a neutral molecule. But fluorine is a weak acid. That's because if you compare oxygen and fluorine, fluorine is more electronegative. What does it mean that as you increase the electronegativity, acidity increases? So we always have to look at what is the resulting atom or the ion strength once you lose a proton. For example, you have H2S. Oh, I can take water and HF, water and HF. So water, if you lose a hydrogen, it would become OH minus. And then the fluorine, HF, when you lose a hydrogen, the resulting conjugate base is your fluoride. This is the Lewis structure, fluoride, right? So between oxygen, so here negative charge is carried by oxygen, here the negative charge is carried by fluorine. The advantage of being more electronegative means once you have this negatively charged, since fluorine is more electronegative, and if you remember the definition of electronegativity is the ability of an atom to pull electron towards itself more readily. So fluorine, that number is 4, which is the most electronegative element, and oxygen, that number is 3.5. Okay, so fluorine is happy to take this negative charge and become and can stabilize this negative charge compared to oxygen. Okay, so therefore fluoride is stable compared to hydroxide ion and will make HF a stronger weak acid compared to water. Same thing between H2S and HCl. Chlorine is more electronegative compared to sulfur. Okay, so once the hydrogen lost, chloride can accommodate that negative charge more readily compared to the sulfur. So hydrochloric acid is a stronger acid compared to H2S. H2S is a weak acid, HCl is a strong acid. Same thing in these other acids as well. That is, as you go across the periodic table, acid strength increases because the electronegativity increases. Now let's look at, so here it says electronegativity increases, so acidity increases. As you go down the group, the size of the atom increases. As the size of the atom increases, bond length increases, so the strength of the bond decreases. It will make the bond break easier. Bond strength decreases, so acidity increases. So you can see here water, H2S, H2SE, H2TE. This is 10 to the negative 8, negative 4, negative 3. So acid strength increases. And all of these are also strong acids. And compared to HF, HF is fluoride is a smaller atom compared to chlorine, bromine, iodine. So the bond is stronger, HF bond is stronger, so it would make it a weaker acid because it will make it difficult to remove the hydrogen compared to the other atoms in the same group. But compared to oxygen, hydrogen, yes, because it's electronegative. But as you go down the group, we are comparing the strength as you go down the group. Since this is a small atom, they are getting bigger, so it make it easier for the hydrogen to give away compared to the HF. Okay, that is the acid strength of non-metal hydrides. Okay, and then we also have acids that contain oxygens, and these oxygens are normally bonded to hydrogen. They are called oxoacids. Acid strength of oxoacids depend on the electronegativity of the central nonmetal. Again, you have a nonmetal and then you have oxygen and hydrogen. We have to look at their electronegativity and the number of oxygen atoms around electronegativity atom. For oxoacids with the same number of oxygen atoms, acid strength increases as the electronegativity increases. Let's look at that over here. So these are three oxoacids. This is the nonmetal connected to oxygen, hydrogen, bromine, oxygen, hydrogen, chlorine, oxygen, hydrogen. Acid strength increases as the electronegativity of the nonmetal increases. Between iodine, bromine, chlorine, excuse me, chlorine is the more electronegative element. So the more stronger acid, when you have the same number of oxygen, is going to be the one that is more electronegative. Okay, so you can see the polarity of between these two elements. Hydrogen is delta positive, oxygen delta negative. Once the hydrogen left, the electronegativity can be more stabilized if you are connected to a more electronegative element. So chlorine is the more electronegative element, so this would make it more stronger compared to bromine, which is more stronger compared to iodine. Okay, electronegativity increases, so the acidity increases when they have the same number of oxygen atoms. And then for oxoacids with different numbers of oxygen atoms, acid strength increases with the number of oxygen atoms. Now let's look at that here. Now you have HOCl, which is hypochlorous acid, and HClO4, which is perchloric acid. One hydrogen, one oxygen, one chlorine. One hydrogen, 1, 2, 3, 4 oxygen and 1 chlorine. Again, when we are looking at the acid strength, we look at what is the stability of the resulting species once the hydrogen is gone. So here, once the hydrogen is left, you would end up oxygen excuse me, with a negative charge. Same thing here. Once the hydrogen is lost, that's what make it an acid. So the negative charge is only stabilized by one chlorine atom here. Whereas this oxygen, these lone pairs can be delocalized. Remember the resonance structures that we drew in Chem 1? So similarly, these lone pairs, meaning the electron density on the oxygen, can be delocalized among these 1, 2, 3 oxygen atoms. It's not in one place. Okay, that will make the perchloric acid resulting perchlorate anion more stable compared to hypochlorite anion. Okay, so this one is going to be more stronger compared to hypochlorous acid, this guy over here. Okay, as the number of oxygen atom increases, acidity increases. Excuse me. In fact, this HClO4 perchloric acid is a strong acid, and hypochlorous acid HOCl is a weak acid. Okay, those are the acid strengths of oxo acids. And then we have another category of acids that generate as a result of hydrated metal ions. How do you make hydrated metal ions? Let's talk about that. Some hydrated metal ions are able to transfer a proton to water. Once the metal gets hydrated, it can give a proton to water. What happens when a proton goes to water? It becomes hydronium ion. Whenever you have hydronium ions in a medium, that will make it an acidic solution. Okay, so these metal ions will form acidic solutions. Let's say you have a metal ion Mn plus. You put it into water. Some water molecules will attract it to the metal cation. It forms a hydrated complex. And this metal excuse me, is small and highly charged. It will withdraw enough electron density excuse me, from the OH bonds of the bound water molecules to release hydrogen ions. Excuse me. Sorry about that. So this is the equation for that. The metal hydrated complex grab water molecule, form another hydrated complex with one hydrogen less, removing that hydrogen to water to form a hydronium ion. Now you may not understand what it means, but let's look at it with a picture over here. Let's say you have aluminum ion. You put it into water. Aluminum is electron deficient atom, so it attracts water molecules from the water medium. Since this is positive charge, when you attract the water, it's the oxygen end of the water molecule attract to aluminum. Okay, because it's positively charged, oxygen is the negative end of the water molecule. Hydrogens are electropositive. Oxygen is more electronegative compared to hydrogen. Now you can see that the electron density from oxygen molecules are pulled towards aluminum ion, right? So as a result, these oxygen hydrogen bonds will become more polar. Oxygen hydrogen bond become more polar. It can happen to any of these water molecules. We are showing you with this water molecule. If this become more polar, neighboring water molecule can come and grab that hydrogen and form. What happens when you take hydrogen H plus ion to a water molecule? It become hydronium ion. So this process releases hydronium ions to the water molecule, making the solution acidic. Now let's see how can we write the new complex that is being formed. Now there are 1, 2, 3, 4, 5 water molecules, nothing happened. So you have aluminum, 5 water molecules, but the one that lost hydrogen, it's not water anymore, it is OH minus, hydroxide ion. So as a result, you will see, so aluminum plus 3, and you have 5 water molecules neutral, and you have 1 water molecule OH minus. So plus 3 and minus 1 will make it plus 2. So as a result, you write the complex as aluminum with 5 water molecules and then OH, and then the charge of the complex is now plus 2. Here it is plus 3 because all of the water molecules are neutral. So that's why you get plus 2 charge here and plus hydronium ion, making the medium acidic. Okay. So acid behavior of the hydrated aluminum ion, it generates acidic medium. Okay, let's see the weak bases. Okay, I think we can cover that in this session too. Weak bases. So far we talk about weak acids. So what about the weak bases? Remember we talk about the weak bases. So let's talk about little bit about the weak bases. A Bronsted-Lowry base. Remember what is a Bronsted-Lowry base? Is a species that accepts a proton. So for a weak base that dissolve in water, let's say this is your base, you put it into water, base attract a hydrogen and will become BH plus, and then the oxygen will become OH minus, right? Remember? So if this is your base with a lone pair that can make a bond, so you have H2O with 2 lone pairs like that. So base goes and take this hydrogen, and the bond here breaks, giving its electron to this oxygen. So now the base will become BH plus, and then the water will become OH minus, because now it has 6 electrons and hydrogen. So BH plus and OH minus. Okay. So we can write the base dissociation equation. The base dissociation or the base ionization constant is given by, instead of Ka, we say it's Kb. We have BH plus OH minus over B. Okay. Note that no base actually dissociates in solution, but ions are produced when the base react with water. No base actually dissociate. Remember, the base doesn't dissociate because base is taking a proton. Whereas acid, HA, it dissociate into hydronium ions and A minus in the presence of water. But what happened with the base, it actually ions are produced when the base react with water, and the 2 ions are BH plus and hydroxide ions. Okay. So these are some Kb values for molecular bases at 25 degrees Celsius. All of these are ammonia derivatives. Remember I talked about earlier, ammonia is a weak base, and then if the hydrogens are replaced with other groups, they also generate weak bases. So this is diethylamine. There are 2 ethyl groups and NH, diethylamine, and this is how the base works. Nitrogen has a lone pair. It take a proton from the water, generate OH minus, and protonated this diethylamine molecule. Kb and pKb given. Remember the pKb, negative log of Kb. And same thing with dimethylamine, 2 methyl groups. How you make ions? You take hydrogen from the water, becoming OH minus, and the protonated base. Same thing for the ammonia plus water. Ammonia has a lone pair. Take hydrogen from water, forming protonated ammonia molecule and hydroxide ions. And their Kb values are given. Okay. Okay, let's look at this example. Dimethylamine, key intermediate in detergent manufacture, has a Kb value 5.9 into negative 4. This is the base that we are talking about, dimethylamine. Kb 5.9 into 10 to the negative 4. You see acid dissociation also, the base forming ion also shown here. Excuse me. What is the pH of 1.5 molar dimethylamine? Now this is a weak base. What do we need to do? First we have to write the equation, how the base generates ions, which is going to be like this. Dimethylamine, in the presence of water, you take a proton and become CH3. This part doesn't change. Nitrogen will have another hydrogen, NH2 plus OH minus. We want to find out what is the pH of the solution, and then we have to write down the Kb equation, and then we have to set up a reaction table and solve for hydroxide. From hydroxide we can calculate hydronium ion and the pH. Okay, we make similar assumptions to those made for weak acids. Since Kb is greater than Kw, anybody remember the Kw for water? Which is 1 into 10 to the negative 14. Okay, and then the Kb here is 10 to the negative 4, which is more higher number compared to the Kw. Hydroxide from water we consider negligible. Since Kb is small, we can assume that the amount of amine reacting is also small. So the initial concentration of the amine is same as the equilibrium concentration of amine or our base. Okay, so let's see how we're going to approach this. First thing is, again, you write the base forming ion equation. Your NH, nitrogen has a lone pair. Grab so here you have a lone pair. This is your water molecule. HOH. I showed you earlier also. Nitrogen takes up this proton and become this NH2 plus and then the OH minus. So this bond will break. Okay. So we can write the Kb expression, which is going to be protonated methylamine hydroxide over methylamine. That's the Kb expression. And you write it down, and just like we did for the acids, you write your ice table. Initial concentration was given as 1.5, and then these are not formed yet, and then the change negative x, positive x, positive x, at the equilibrium 1.5 minus x, x. And since Kb is small, we consider this x is negligible, so small compared to 1.5, so 1.5 minus x equals 1.5. Okay, so the Kb expression is this. We were given Kb, and this is also, this is your x, this is your x. We'll make it x squared. It's difficult to say x squared. You try doing it, your tongue will twist. Okay, it's a tongue twister. X squared. Try doing that. Okay, maybe a few times. You will have fun. So 5.9 into 10 to the negative 4, and you divide it by initial concentration, which is 1.5. So you multiply these two and get the square root. You can find out the x, right? Like this. So you can find out the x. To do this calculation and see if you're going to get x as 3 into 10 to the negative 2. And then we can check to see the assumption that we made is valid. So this is the x amount, and you divide it by the initial concentration times 100, 2%. So our assumption is justified. Okay, what we want to find out is the pH of the solution. So we found the hydronium ion concentration. If you know the hydronium ion, how do you find the we want to find out the hydronium ion concentration. We know the hydroxide ion. Remember, OH minus times hydronium ion is going to be the Kw, which is 1 into 10 to the negative 14. So we can find out the hydronium ion concentration. That is going to be Kw over hydroxide ion concentration. And Kw is 1 into 10 to the negative 14. Hydroxide O into 10 to the negative 2. So you can find the hydronium ion concentration. And then the pH is going to be negative log of this one. So you can find out the pH. So that's how you find pH of a base, weak base. Okay, so let's stop here.